as you'll see there, the title of the presentation is the automotive industry in the slow lane, and is also the title of this particular session. It's a slightly provocative title, but I think you'll see as we go through this that the auto industry maybe needs to change a bit faster. I'm going to cover, first of all, I think what we mean by Industry 4.0. I'm going to talk a little bit about what's going on in some other sectors, and then the opportunities in automotive. And then I'll finish off with the initiatives currently underway by the Auto Council and the Institute of Digital Engineering. So, what do we talk about industrial revolutions? The first industrial revolution was mechanization from horsepower and wood to coal, iron, steel, and steam engines. The second was all about mass production, so mass production and assembly lines. Third was the information age, connected devices and people via the Internet of Things, and the data explosion, going from mainframes to everybody with connected information via their mobile phones. Now, the fourth industrial revolution is often called connected intelligence. So that's making sense of and extracting value from the information age. In other words, artificial intelligence. So the big difference between Industry 3 and Industry 4 is the rate of change. Whereas Industry 3 took a number of decades from mainframe computers back in the 70s and 80s. I remember when the company I worked for introduced its first mainframe, all the way to this mobile connected population, maybe 40, 50 years. Industry 4 is going to happen much faster. So from big data platforms going through machine learning, ubiquitous user interfaces, and then increasingly tools with embedded knowledge, moving to full digitalization is going to take years rather than decades. I'll talk about what we mean by digitalization later, but perhaps it's important to cover some key definitions first. So terminology can be quite confusing. You've all seen these particular definitions or terminologies: big data, machine learning, deep learning, and artificial intelligence. Big data is quite difficult to define, but one of the best definitions I've heard is data that consists or contains more than about 1 million columns of data, where deterministic analysis becomes quite difficult. Machine learning at its most basic is the practice of using algorithms to define key characteristics or parameters, then identify correlations learned from large data sets, and then make a prediction based on a new set of input data. Deep learning is really an extension of machine learning, where you've got huge neural networks and you're able to use less of these algorithms to help you define what you're trying to predict in the first place. So deep learning is about the depth or number of layers in a neural network. Artificial intelligence is a well-used term, but difficult to define. And general AI, as often defined in films, is really still science fiction. It's something that cannot be developed at this stage. We just don't have the technology. However, we do have some forms of narrow AI. Good examples are the techniques that are being developed to provide automated driving in mixed traffic conditions, and also, under some circumstances, image classification and defining what might actually be in an image and what it means. So I spoke earlier about digitalization. What is digitalization? There are a number of definitions again, but perhaps the most relevant for engineering is what I call turning a physical test or labor-intensive process into a virtual or digital form to add value and increase efficiency. So it's really about saving time and using our knowledge to get to the answer faster. So if we move on to some other sectors and what's going on there, let's talk initially about the financial technology sector, or FinTech. It's a huge sector now. The market is expected to grow to over $300 billion by 2022, big growth rate. And the use of AI in FinTech is now around 7 billion and expected to reach over 35 billion by 2025, a huge growth area. And it's worth noting that the UK is very much involved and a leader in this technology, particularly in the City of London. An example of how this is used when we talk about AI for agent-based trading, many financial trading companies now have these AI systems where they have a complete model of the entire market, right down to the individual trader, that can respond to data and inputs. And they use past trades, past market information to develop and tune behaviors right down to those individual trader characteristics, and able to predict market movements. So they'll look at perturbations, things that might happen, various announcements that might be made, and be able to predict where those funds might go. So you'll often see that these are now used for hedge funds. And I have heard from some people in the city that some of these systems have put some of the human hedge fund operators out of business. Well, I also hear that there is still a little bit of a competition between humans and AI. Also interesting to note, companies like Siemens use AI and machine learning to forecast and manage renewable energy resources and future raw material prices to try and buy at exactly the right time. So we all know we have big challenges. We've got to improve productivity. Despite increasing product complexity, we've got to get product development costs under control, 1 to 2 billion now for a new product launch. And the connected autonomous functions that are coming, how do we optimize, validate, and certify those without the ability to do vast amounts of physical testing? However, there are real opportunities enablers. First of all, the exponential growth in computing capabilities, the growth of machine learning and artificial intelligence, and flexibility in advanced manufacturing technologies. All of these things bring huge opportunities to develop new processes that are more efficient. A good example of this is the product development process. Now, many automotive companies have different variations of this kind of process. You roll around this pie chart as I've drawn it here, from concept design, proof of concept, definitive design, product optimization, and validation and verification, right through to production ramp up. This whole thing can take about 4 to 5 years to complete. And we have to roll this whole system around every time we want to do a new product. However, we're now trying to roll this whole thing uphill because there's increasing product complexity. So the whole principle behind digitalization is to reduce the number of phases, make many of them run much more in parallel, and become much more automatic in how you move from one stage to the other. So we move maybe from generative design to virtual optimization and validation before you get to production ramp up. And the predictions are that maybe we can change that 4 or 5 year term to 1 to 2 years. Worth pointing out, vehicle software is now emerging as the critical path for new product development, and that does lend itself to this whole virtual optimization process. To achieve this, we're going to have to change the way we work, and we're going to have to look at how we increase the amount of validation we do in a virtual environment from where we are today right through to maybe 90 or 95%. In terms of tools and processes, from the discrete connected tools we have today, we're going to have to move to intelligent design and auto-optimization. In manufacturing, from where we are today, digitally optimized machining and assembly, right through to reconfigurable production. In terms of data and knowledge, data share and interrogation is where we are today, but largely all of the knowledge is based in the people we have in our organizations. In the future, we want to embed that knowledge in the design tools. And as far as skills go, we need much broader engineering specialists, with moving towards interconnected AI and human intelligence. How do we use these tools and embedded knowledge much more efficiently? I should point out the IDE will be leading a detailed national road mapping program for digitalization over the coming few months. So as an example, in machine learning and AI in product development, at the moment it's mostly associated with automated driving, but there are significant opportunities to move forward. So knowledge-based design, putting the knowledge from past product design, performance and manufacturing in our design tools, and going to auto-optimization. So rather than doing design, analysis, redesign and reanalysis, making design and analysis part of the same tool, and design as an output from a component or product based on the attribute requirements. And of course, manufacturing and cost implications can be embedded in the design process. So we know exactly how it can be made and how much it's going to cost right from the early stages. So finally, I'll move on to some comments on what we're actually doing in the auto industry at the moment, particularly from the Auto Council and the IDE. So the Automotive Council has recently restructured. It was formed in 2009, but we now moved on to a new approach where we're focusing on 3 core missions: the transition to zero, connected automated mobility, and advancing digitalization. Each of those missions has an industry lead and delivery lead. And for advancing digitalization, we have Mark Matheson from McLaren, who's our industry lead. He'll be speaking later, and Bradley Biggs, who's our delivery lead, who you've already heard from. And the mission there is delivering world-class UK automotive capabilities through digital innovation. Another major initiative underway is the Brunel Challenge, and it's a plan for UK engineering to lead the world by delivering ever more complex products in half the time and for half the cost. It's an interesting program, and we join forces with a number of other sectors. So the Defence Partnership, the Advanced Aerospace Group, Maritime, Energy, and the High Value Manufacturing Catapult. All of those sectors face exponential growth in system complexity, and the need for knowledge-based high-value design and virtual product development and validation is absolutely required, particularly throughout their entire supply chains. So how do we make the supply chains work in this virtual and digital world? It's about harnessing new technologies such as AI and big data to transform our agility, fidelity, and efficiency, and really moving forward our productivity, which is a key requirement for growth. Overall, our proposal is for a multifaceted 5-year, 350 million program, 55% funded by industries themselves. We have a number of fast start projects that are ready to go and that build on existing national infrastructure and capabilities. Based on what's been going on recently with COVID-19, we've learned quite a lot on how to get things going, get started through the ventilator initiative that the automotive industry got involved in. So we put forward an accelerated 50 million Brunel fast start proposal to government as well, called the Brunel Slingshot, really to get things moving much faster and to ensure that we create value from this entire program. But however, we will need a new set of skills. So the future interconnected digitalized economy will need a new set of engineering and business skill sets. So what do we need from the future generations of engineers? Many of these are brought up in social media, virtual reality gaming. I hear my son every day on his computer game in his room, connected to the real world outside, hasn't left the room for ages, it seems like. They have a broader view of environmental responsibilities. They have seamless social interactions via the digital and physical world, and they've also been driving the growth of on-demand services, which is a big change in how we might operate. But we have ever more complex engineering challenges with complex systems interactions, much more reliance on digital tools and techniques, requiring a knowledge of multi-physics challenges and where those opportunities might be. And we're increasingly seeing domination of mechatronics in just about all areas of engineering. So what do we need from future skills? We need capabilities in digital tools and how to validate solutions, an understanding of the physical process, but also how you digitalize those physical processes and use them in a virtual world. We do need a broader understanding of all engineering disciplines because we have so many more interactions that take place. And of course, we will be moving to open innovation in our digitally connected world. Fortunately, we've got Sir Brian Burridge talking later this week, and he'll have a keynote on this topic in the Friday webinar. So I'll just finish with a final message here. And the final message comes from somebody we all knew. If you always do what you've always done, you always get what you've always got. And that was from Henry Ford, founder of the Ford Motor Company. How prophetic. But we do need to keep moving. We do need to keep changing. So that concludes my presentation. Thanks very much.